This is a P1 video looking at the specific heat capacity required practical. Now, specific heat capacity is defined as the amount of energy needed to raise the temperature of 1 kilogram of a substance by 1 degree C. Now, on this picture you can see at the moment, we can see the setup for the experiment. We have our metal block with a thermometer and a heater. The heater is connected to a power pack, and within that circuit as well we have an ammeter in series and we have a voltmeter in parallel. Okay, and we've got lots of different blocks that we can use. Okay, some of the blocks we've got here, we've got don't know if you can necessarily read them, but we've got steel, iron, copper, brass, and set up on the equipment we've got aluminium. And all of those are 1 kilogram blocks, but obviously being different metals, they've got different densities, so therefore we see that they have a different volume each time, okay? But they're all, if we put them on the scales, they're all a 1 kilogram block. Now, what I've got set up on the experiment here is, this one is my voltmeter, okay? It's a multimeter that's been set so I can use it as a voltmeter, and if we follow these two lines, these two wires, they both go straight into the power pack. Now, I could read the voltage straight from the power pack, but it's not very accurate to measure from here. Here I've got high resolution, so it's a very precise measurement, and I can see that that is kind of fluctuating around, so I'm going to wait a second. At the moment it's reading 8.94 volts. So I'm going to write that down, 8.94 volts. And then within my circuit I have this ammeter, so that's in series. This is parallel. I could literally just have that voltmeter connected to the power pack, and so long as I don't change this, I could then remove the voltmeter if I wanted to, because I know the voltage will stay the same. Okay, so there's a voltmeter in parallel, and my ammeter is in series here, and this is currently reading 2.34 amps. And then my ammeter comes along here, the wire to the ammeter, the wire from the heater going into the block, and then the heater back into the power pack. Okay, so let's just remind ourselves on that diagram. Okay, so we've got the voltmeter that is literally just going this way across the power supply. We've got the ammeter in series, and we've got the heater coming off from that power supply as well. Okay, so technically this voltmeter is looking at the voltage across the heater, but it would be the same if we had the voltmeter across the power supply here. It would give the same voltage. Okay, so we've technically got the voltmeter just here, but having it just here is still looking at the voltage across the heater. Okay, so let's go back to our setup of information then. So, our equipment. We have so far got the voltage and the current. This heater is on, it's now heating up this aluminium block. I've got here a thermometer which I've checked has got no air bubbles because that would give me an inaccurate reading, currently reading 30 degrees. In order to transfer the energy as well as possible from the block, from the heater through the block to the thermometer, I'm going to add a small amount of water just into where the thermometer is, and that helps with the transfer of heat. Okay, it doesn't need a lot, that's now full. And this is an example of using multi-step calculations. Okay, so the first information that I've got is I've got that the voltage is 8.94 volts, and I'm multiplying that by the current, which is 2.34 amps. Okay, now I always say that the calculator is our friend. Even if it's a simple calculation, it's really useful to make sure we use the calculator, don't lose silly marks. Okay, and from that I write it out exactly as it is on the calculator. 20.9196 watts. So I've calculated the wattage, okay, using the voltage, using the current. Now that power, that wattage is going to go into my next equation. So 20.9196 watts. I'm going to keep all of my decimal places just so that I can, you know, not lose anything as I go on. And then I have set it up. I've allowed the heater to heat up a little bit. Haven't actually done anything with my stop clock yet. I'm going to start my stop clock and I'm going to let that run for 20 minutes. Okay, and I'm also, now I've let it go, I'm going to look at that thermometer and that's reading 34 degrees C. So that's my start temperature, okay? And I'm running it for 20 minutes. I've got here a scrap of paper which I'm adding all my bits of information onto. Now, let's go back to our calculations. The time needs to be in seconds. So I know I'm going to run it for 20 minutes. Times that by 60 seconds gives me 1,200 seconds that it's going to run for. Now, multiplying those two together, I can work out how much energy I've put into this set of equipment, how much energy I put into that aluminium block, okay? So, let's multiply those together. Okay, and that gives me an energy of 52 joules. Okay, so that's how much energy I've put into the block. I can now transfer that information. Okay, so change in energy, that's how much energy I'm putting into the block. Okay, I know that the mass is 1 kilogram. Specific heat capacity is my unknown, okay, and we know from the formula triangle just here that we've got the mass, we've got the heat capacity, here's the energy, and this is change in temperature. Okay, so the triangle there represents the change, and the temperature change I will find out in 20 minutes time, so see you in 20 minutes. Okay, it's almost 20 minutes later. You can see we're on 1925. Just going to, while we're waiting for that to get to 20 minutes, just going to say about these multi-step calculations. So we worked out the power and we put the power into this equation. This equation we worked out the energy and then we put that into this equation, okay? And we can see on the timer now, nearly there, 4 seconds, and let's look at the temperature now, and it's 52 degrees. Okay, so into my equation here I've got the temperature change, so it's going to be 52 minus 34. Always use a calculator, however silly it seems, okay? And that is a difference of 18 degrees, okay? Now I need to use my formula triangle now because I need to isolate specific heat capacity, okay? So C equals energy, which is, if I write out the whole equation first, energy divided by mass times change in temperature, okay? So I covered my finger over that one, gives me energy divided by mass times change in temperature, and let's put that information in. And let's see what we get from the calculator. If we are doing this and our number is not 1 for mass, be really careful, don't just plug it straight into the calculator. This bit needs to be in brackets, otherwise everything goes wrong, okay? gives me an answer. Let's do it in red. Okay, now that is the specific heat capacity. Let's look at the units here. Okay, joules per kilogram degrees C. Okay, now it's not too bad. It's not too bad. I'm not too out. Okay, the specific heat capacity for aluminium is actually 900 joules per kilogram degrees C. Okay, so my number is a bit bigger. Now, let's talk about reasons why we don't actually get the most accurate measurement of specific heat capacity. So, energy losses. We didn't put any insulation around the aluminium block. There was quite an exposed section of heater. Okay, about half the heater is actually exposed. All of that heat energy is being lost to the atmosphere. Okay, I did a small amount of preheating of the heater before use, but if it was being heated from cold, then there's a lot of kind of time that's passing when actually the heater isn't working at its kind of normal capability. And also I try to fix it by putting some water in with the thermometer. That poor transfer of energy between the heating element and the metal block will also cause some of the maybe the thermometer to not go as high as it should do. Okay, so there'll be some inaccuracies there as well. Hope you found that useful. Thank you.